Welcome to today's paper reading. Today's paper is titled, Instruction Tuning with GPT-4. This paper was published on AR14 by Baolin, Peng and colleagues from Microsoft Research. In this paper, the authors present a novel approach to fine-tuning large language models, LLMs, using instruction following data generated by GPT-4. This method involves creating 52,000 English and Chinese instructions, which have demonstrated superior zero-shot performance on new tasks compared to data generated by previous state-of-the-art models. The authors also emphasize the importance of collecting feedback and comparison data from GPT-4 to facilitate comprehensive evaluation and reward model training. Notably, the data generated by GPT-4 and the accompanying codebase are made publicly available, contributing to the transparency and advancement of the field. Large language models, LLMs, exhibit remarkable capabilities such as in-context learning and chain-of-thoughts reasoning. To enhance their ability to follow natural language instructions, researchers have employed various instruction tuning methods, including human-annotated prompts and self-instruct tuning. Recent successes like ChatGPT and GPT-4 have demonstrated the potential of instruction tuning to improve open-source LLMs like LLaMA. For instance, Stanford Alpaca and Vicuna have utilized large datasets to enhance their instruction-following abilities. The data collection process involves utilizing various sources such as public databases, private partnerships, and crowdsourced data. The types of data collected include structured, unstructured, and semi-structured data. Ensuring data quality is crucial, focusing on accuracy, completeness, and consistency. The instruction tuning process involves generating datasets based on 52,000 unique instructions. These datasets include English and Chinese instruction following data, which are generated using GPT-4. Additionally, comparison data is created where GPT-4 rates its own responses and compares them with those from GPT 3.5 and OPTIML, which is used to train reward models. Another dataset focuses on unnatural instructions, using a subset of 68,000 instruction input-output triplets to quantify the performance gap between GPT-4 and instruction-tuned models. Figure 1 provides a detailed comparison of the responses generated by GPT-4 and GPT 3.5. Subfigures A and B display the root-verb-noun pairs for GPT-4 and GPT 3.5, respectively, highlighting the inner circle as the root verb and the outer circle as the direct nouns. Subfigure C compares the frequencies of the top 25 verb-noun pairs between the two models. Subfigure D illustrates the distribution of output sequence lengths, showing that GPT-4 tends to produce longer sequences compared to GPT 3.5. This analysis is crucial for understanding the differences in output characteristics between GPT-4 and GPT 3.5, which can inform further tuning and optimization efforts. Figure 2 illustrates the distribution of comparison data used in the study. This data is generated by GPT-4, which assigns scores ranging from 1 to 10 to different responses to a given prompt. A reward model based on OPT 1.3b is trained to rate these responses, aiming to predict a scalar reward. The figure visualizes the distribution of these scores, providing insights into the quality and variability of the responses evaluated by GPT-4. In this section, we present the experimental results of our study. We utilized 3 key datasets for evaluation: User-Oriented Instructions 252, Vicuna Instructions 803, and Unnatural Instructions. These datasets were chosen to assess the model's ability to follow instructions across various tasks. For human evaluation, we adopted the alignment criteria of helpfulness, honesty, and harmlessness, which are crucial for evaluating how well an AI system aligns with human values. Additionally, we employed GPT-4 for automatic evaluation, comparing our models against state-of-the-art systems and examining performance in Chinese to ensure a comprehensive assessment. Figure 3 presents the results of human evaluation on the alignment quality of instruction-tuned large language models, LLMs. The evaluation is based on the helpfulness, honesty, and harmlessness, HHH, criteria. In the comparison between LLaMA models fine-tuned on data generated by GPT-4 and GPT-3, Alpaca, GPT-4 significantly outperforms in the helpfulness criterion with 54.12% of the votes, while GPT-3, Alpaca, only wins 19.74% of the time. For honesty and harmlessness, the majority of votes fall into the tie category, indicating a close performance between the models. When comparing GPT-4 instruction-tuned LLaMA models against the original GPT-4, the results show a consistent performance across the three criteria, suggesting that the instruction-tuned LLaMA models perform similarly to GPT-4. Figure 4 presents the performance comparisons of various models evaluated by GPT-4. Each bar in the figure represents the evaluation result between two models, with the sum of scores computed and reported, totaling 800. The relative score is expressed as a percentage, calculated as the ratio against a strong opponent model. Subfigures A and B show the comparisons of responses from LLaMA GPT-4, ranked by the reward model, with B indicating the baseline decoding result of one response per question. Subfigures C and D compare all chatbots against ChatGPT and GPT-4, respectively. This figure highlights the relative performance of different models in response to GPT-4's evaluation criteria. Figure 5 presents a detailed comparison of the performance of various models in following Chinese instructions as evaluated by GPT-4. The figure is divided into three parts, A and B, where models respond in English and their responses are translated into Chinese, and C, where models directly respond in Chinese. Notably, the translated Chinese responses in A and B show a higher performance compared to the generated Chinese responses, likely due to GPT-4's stronger English instruction following ability. This observation highlights the consistency of GPT-4's evaluation metrics across different languages and models. In C, the results demonstrate how models perform when directly asked to answer in Chinese, providing a comprehensive view of their capabilities in handling Chinese instructions. Figure 6 presents the Rougeau scores for unnatural instructions evaluated across 9,000 samples. The instructions are categorized into four subsets based on the length of the ground truth response. The mean Rougeau values are indicated in the legend, and the difference in performance compared to GPT-4 is shown on each bar for each group. Notably, LLaMA GPT-4 demonstrates a closer alignment to GPT-4's performance compared to Alpaca, particularly in scenarios where the ground truth response length is longer, suggesting better instruction following in more creative contexts. Instruction tuning of large language models, LLMs, aims to enhance the quality and scale of instruction following data, foundation language models, and evaluation benchmarks. For instance, models like FLAN and scaling models are built to improve these aspects. Additionally, Prompt Source and its public pool of prompts P3 contribute to a growing collection of prompts, while T0 models are trained on P3 through multitask prompted training. The OPTIML bench, which includes FLAN, supernatural instructions, and unified SKG, is another comprehensive benchmark used in instruction tuning. On the open source front, efforts have focused on creating general-purpose, text-based assistants aligned with human values. Early foundation LLMs include Bloom, GPT-J, GPT-Neo, OPT, and LLaMA. Projects like Open Assistant and Alpaca/Vicuna are built on these models to align them with chat-based assistants. Furthermore, OpenFlamingo and LLaMA adapter connect LLaMA with image inputs, paving the way for open-source multimodal LLMs. This paper highlights the effectiveness of instruction tuning using GPT-4. The dataset used includes 52,000 English and Chinese instruction following instances generated by GPT-4. The base model used is the 7 billion parameter LLaMA model. For comparison, Vicuna, which uses a 13 billion parameter LLaMA model, collects around 700,000 conversation turns. To further enhance performance, the authors suggest combining GPT-4 data with ShareGPT data and training even larger LLaMA models. Additionally, the paper explores the use of reinforcement learning from human feedback, RLHF, where a reward model is used in the decoding stage to provide feedback for LLM training, potentially through reinforcement learning using machine-generated feedback. In this section, we acknowledge the significant contributions of Guiying Wang, Haoyan Liu, and Hao Qing, whose valuable discussions and experience sharing were instrumental in the instruction tuning of language models. We also extend our gratitude to the LLaMA team for providing access to their models, which greatly facilitated our research. Additionally, we recognize the broader research team, including Amanda Eskel, Yuntao Bai, and Anna Chin, among others, whose collective efforts have been crucial to the development of this work. Thank you for watching.